All right, and looks like we can get started here. Hello, everyone, and welcome to the next session. This session will be led by Xuan Tao, a data scientist at Walmart Labs. So please join me in welcoming him to the virtual stage.
Hi, thanks for the introduction. So I'll just jump to the topics about the presentation today. I'm Xuan Cao, and the presentation I'm going to make today is about using classifiers to improve the performance of a segmentation model. So it's a case study based on a Kaggle competition which I joined. So a little bit background regarding the competition. So the competition is called Understanding Clouds from Satellite Images. It's a competition held 8 months ago. The idea about the competition is that so we were given lots of satellite images about clouds, and we are asked to give classifications about which regions belongs to like a fish, flower, graver, or sugar in the image. So basically, we need to make 4 class classifications for the image. And the metrics used in this competition is called dice coefficient, which I will explain a little bit in the following slides. So before we jump to the data and everything, I think there are 3 questions I usually ask myself. So first, we need to get a big picture about the data set and the problem definition. And the second is, of course, the most important, what are the metrics we want to use to evaluate the model performance? And the third is, what is the state-of-art methods to approach the problem? So if we look at the data, we realize that because we have, so basically for each image, we need to make classifications about 4 different classes. So if we count the clause type for each image, we find that all the image has at least 1 class. Basically, one of the channels is not empty. And there are few that have 4 different types of clause for the image. And on the other hand, if we examine the class types number for the clause, we see that it's almost uniform distributed. So basically, the 4 classes are uniformly distributed among all the different images. So the idea is that basically, given this satellite image about the clouds, we want to show, for example, this region belongs to fish, and this region belongs to flower, and then all this region may go, and then this small region belongs to sugar. So we need to make this kind of predictions. So basically, the problem is called a multi-class image segmentation problems. This is multi-class because for some, you can see that for this particular example, the graver and the flowers, they have some overlap. If it's multi-label, then means that for one region, they can only belong to like 1 class, not like multiple class. The next question is about what are the dice coefficient. If you search on the Wikipedia or whatever, they will give you the dice coefficient formula in this way. It's equals to the union of these 2 regions and divided by means the intersection between of the two regions divided by the union of the 2 regions. It will be easy to understand if you look into like schematics. So basically, imagine the ground truth label is marked by this X, and then you predict another region called Y. Then basically the dice coefficient equals to the yellow region divided by the summation of the 2 green and red. So an important thing to keep in mind is that this dice coefficient put large penalty on false positive. So imagine for an image there's no ground truth label, but still you give some predictions, and then the dice coefficient is 0. So this is very important to keep in mind. And on the other hand, if you give a correct prediction about this image, saying you don't give any predictions, then the dice coefficient will be 1. So what are the state-of-art methods to tackle our image segmentation problem? If you search on the literature, you will realize that there's a bunch of things called UNet, which is first introduced to do medical image segmentation problem. So basically, in this approach, when you have some image coming into the model, it will do a bunch of scale down and make it to like a smaller region, and then we scale up again. And there also skip a bridge to put the information of the raw image to the decoder part. And then eventually this thing are going to a scale up region. and get into the original resolutions, and therefore you can get the segmentation results from the output here. There's another group of family called feature pyramid network, which carry very similar concept where you have some bunch of convolution networks to scale down the image to like a smaller pair, and then you do another part of scale up, go back to the original resolution and give predictions. So knowing all this information, we start with building a baseline model. In this particular case, the baseline model I use is FPN with backbone using ResNet 34. So in the model, for these three layer, we call it decoders. We use the ResNet pre-trained ResNet 34 blocks as decoders to basically extract information from the image. And then we're going through typical scale up region to go back to the original image resolution level. And then we generate predictions. So, and then finally, we can make the prediction about 4 channels, each channel representing for like one of the class. And for this particular case, the loss function I start with is the classical binary cross entropy loss. And this baseline model reached around 0.0464 on the test set for the dice coefficient. So the next question asked is how we can improve the model. To understand where the model went wrong, we need to revisit the predictions from the validation set. So after examining the validation set, I realized there are 2 kind of root cause for the performance, for the bad performance. First is that the model gives false positive predictions. As I talked about this point a few slides ago, if you make a false positive predictions from the model, then the dice coefficient is 0, which is a huge penalty for the model. Another thing is that sometimes the model may give not very accurate prediction mask. For example, for here, the red region is the prediction from the model, but the like a light green region is from the ground truth label. So you can see that we don't have like a very accurate prediction, so therefore the dice coefficient is low. So how we can improve the problems, improve these 2 points. So I will tackle them one by one. So first, to eliminate those false positive predictions, one may naturally come to the idea that we can introduce a classifier at an image level. So the idea is that for the baseline model, we have some image coming into a segmentation model, which is an FPN using ResNet 34 based on the BCE loss, and then we get some base predictions. So we can build another model, which is a classifier. We may use similar backbones. The classifier's job is to predict whether we have one of these 4 class call type in the image or not. So basically, we'll generate a prediction about the probability. And if the probability is smaller than 0.5, we can say, okay, the model says there may not be this type of class in type of clause in the image. So we can set those corresponding channel to be empty, prediction as empty. Therefore, we generate the final predictions. Another way, so this approach will tackle the problem of false positive predictions. Another point is that we want to make the predictions about those positive masks to be accurate. So the idea here is that we can use a modified loss function to improve the performance. I will elaborate why we can do it using these methods. So if we look at the loss function we use here, we use binary cross entropy loss to optimize the model. But however, this binary cross entropy loss is not optimizing the dice coefficient directly. The reason is that if you look at the dice coefficient form, it's actually equivalent to an F1 score at a pixel level. So, you know, the dice coefficient, I mean, the BCE is more or less optimizing the accuracy, which is not the same idea as F1 score. So how can we do that? The idea I propose here is using soft dice loss. So basically, the idea is that we can generate the predictions at a probability level, and then if we have the ground truth label, we can do the intersection by simply do the multiplication between the predicted probability and the ground truth label And then we can also get a union from these two by simply sum them up. And then we can define soft dice coefficient as the division between these two, and we can get a loss function in this way. So a challenge is that the dice coefficient is not very, this kind of dice score is not very good when we have an empty channel, meaning that when there is the ground truth is all 0, and then the dice coefficient become very unstable. So the idea to solve the problem here is that we only apply this loss function to those positive channels, meaning if you have the ground truth label tells you there is if there is a non-empty mask on the image, then we apply this loss. Otherwise, we just do not count the loss from this kind of the corresponding channels. So this is the code here. Snippet here shows the implementation of this kind of positive loss using PyTorch. So basically, we pass the ground truth label at the image level to the function, and if the ground truth label is positive, then we count it. Then we only count those loss function from those place where we have this the non-empty mask. So adding this part to the model, so this come to our final framework. So in the final framework module, we have two segmenters. One is trained with binary cross entropy loss. The other is trained with this positive only dice loss function. So the predictions from the first segmentation is we call it base predictions. And then we use the second one to modify the positive mask, because this one is better at accurately capturing the mask outline. And finally, we use the prediction from the classifier to remove the false positive predictions. And by doing this kind of by using the results from multiple models, I managed to increase the dice coefficient from 0.64 all the way to 0.67. So there are other things worth mentioning in improving the model performance. First part is getting more data to train the model. So this is a very important point when you are dealing with image computer vision problem, because we have lots of transformation to tweak the image a little bit, where do not change the model label. So for example, the satellite image come here, we can flip it vertically, but this does not change the natural that this region still belongs to like gravel or sugar. This is what people usually call image segmentations. You can do flip vertical, flip horizontal, and then you can do some small twist, rotation, things like that. Another type of thing we call that once you get the predictions training from the training set, get a model, you get the predictions, and then you can take the pseudo labels predicted by the model which are actually on the test set, which you basically don't know that, but you can pick those ones with that are model prediction with high confidence. So basically, by this way, it's like you hire another labelers to help you label a bunch of new images. Then you can include these things together with the training set, and then retrain the model. So basically, you expand the training space of the model. Therefore, you can get more data, then you can usually get a better model. Another part is doing the ensemble. So for example, this is a test image. We call this is called test time augmentation. So imagine this is a raw image you want to give the predictions. But as we mentioned, if you flip the things around, this does not change the nature that some region belongs to gravel, some region belongs. So you can flip the image, get the predictions, and then flip it back, and then you can do the ensemble between these two. So for example, pixel belongs to gravel, the other belongs to fish. Then you can do the ensemble between these two to generate the final predictions. Level of ensemble is at a model level. So for example, you can train the model build of different backbones like UNet. You can kind of ensemble together, you get the final prediction. So this basically is like you collect lots of voters together and ask them to vote on the predictions, and then collect basically the people most of people vote for one, then you say, okay, this one is the other may not. So this also makes the model generates better, which is a better way to improve the model performance. So this is the overall strategy, all the strategy I use and the corresponding improvements. So the baseline model plus remove false positive on the mask on the mask area. This one get us to the baseline performance baseline level at 0.64, and we after adding the another segmenter and the classifiers, it increased all the way to 0.66, and after that we try different backbones because Resonance 34 is a relatively simple backbone. It cannot handle complicated information, so we can use like more complicated or larger model like ResNet 40 or even EfficientNet E7, and then to increase the model performance. And then after that, I did some ensemble at the model level to finally squeeze out the model performance. At the end, there is pseudo labeling, which boosts to the final stage. And the approach I used get me to land at the third place of the overall results, which is like a really great result for me. And so takeaway message from the presentation I make today is that first, use classifiers properly could improve the segmentation performance significantly. And the second point is that appropriate loss function is critical in building high performance computer vision models. And at the end, I think this is the most important thing, that you always need to examine the wrong predictions from the validation set. And then you can get an idea about where the model went wrong and then make the corresponding adjustment to the model. And therefore you can make the model performance better. So thanks for attending my slides, and that's all I want to share about the technical details about one of my cargo winning journey. And I'd like to take any questions from here. Okay, the first question, what about transfer learning? Basically, it's everything here is used transfer learning. When I'm using, for example, ResNet 34 as a backbone, I did not train the ResNet 34 from scratch. I just used the pre-trained model from the ImageNet, so it makes the learning everything much faster. Yeah. So almost everything, I think, for the image classification problem or the computer vision problem, using the pre-trained network from the ImageNet is a standard way for most of people, unless you have some very specific task, like for medical image, you may need to train another backbone yourself. Since usually for medical image, it may be possible to collect tons of image yourself. Yeah, but still, because when you transfer the model to this particular task, you also make the backbone part trainable. So actually, the model is still it also includes a fine-tuning stage. Basically, the model also learns some particular some specific things regarding this particular data set. Yeah. Did I try DeepLab v3? No, I didn't try that. I didn't try DeepLab v3 for the segmentation. I just used this the UNet and FBM for this particular case. Yeah. Any other questions? Yeah, thanks for your question, Vladimir.
All right. Other questions? Then thank you everybody for attending. I hope you enjoyed that presentation as much as I did. And we do have a couple minutes into your next session, so you can go check out networking, check out booths, ask any last-minute questions that you might have. But otherwise, thank you very much for. Hope you enjoy your next session. The rest of the conference.
There's another question. I'm confused about pseudo. Yeah, I'm confused about pseudo labeling. How would that expand the training data set? Wouldn't it expand the testing data set? Where because for here we have a test set which are unlabeled data set, right? So basically using pseudo labeling is like a kind of labelers to label those unknown data set, and then you can get like bunch of data training samples with new label. So if you include that into your training set, then basically you are expanding your training data set. So it's like including some data from the testing data set to the training data set. So that's basically the idea behind pseudo labeling. And next question from Wender, what tool did I use for labeling? I'm not sure which part you are asking. If you are asking about ground truth labeling, I'm not labeling the ground truth labeling. It's coming from the competition organizers that provide us with the labels. I believe the label comes from crowdsource. It's they use some kind of crowdsource website, ask volunteers to label the data for them, and the mask region, I believe, usually comes from multiple labels. So that's why you can see it's not like a very nice looking rectangle or things like that. It's not a regular shape. Yeah, I'm not sure whether I answered your question correctly even there.
All right. Well, if anything comes up, we have about 2 more minutes, so you can always write it in the chat. But otherwise, yeah, feel free to get ready for your next session. Thanks for coming, everybody, and I hope you enjoy your conference.
Yeah, thanks for coming. Okay. The test set still remain. Next question. The testing set will still remain the same, right? The way we are not mixing the training and test. Well, the testing set remain the same, but since some of the samples in the test set, you model have higher confidence in those things. So that's why we include those things into the training set. And it's kind of mixing the training and the testing, but you are basically mixing the training set with some high confidence predicted testing set. That's basically the idea behind that. It's like you hired another labelers to label those testing set, and then you pick some parts of the labeled samples which people are confident about the labeling, and then you include this part into your training set. So that's basically the idea behind that. Let me know if that answers your question, Chelsea.
All right, we do have to call it there because the next sessions are beginning. So thank you so much, everybody, and I hope you enjoy the rest of your conferences.